All right, so these vectors are not collinear. They are not perpendicular, right? But it doesn't mean I don't treat them in the same way I did the other two kinds. I'm still going to draw them tail to head. But what I'm also going to do is identify how far west and north or west and south they go at the same time, right? So first step here is to obviously draw out the vectors. My first vector is 220 kilometers at 30 degrees north of west. Right, so I'm going to start my drawing over here because I know I'm going west. Okay, I'm going to draw a compass rose on here just so I make sure that I'm drawing everything the right way. So here's my starting position. I'm going to go 220 kilometers at 30 degrees north of west. That means that angle is measured from due west. So I'm going to draw a reference line that points due west so that I can go 30 degrees north of it and figure out where my line should go. All right, so this line is 220 kilometers long. It's angled 30 degrees, and it has a horizontal, or X, and vertical, or Y, component. Okay? The Y component will be the north-south part of it, and the X component will be the east-west part of it. After that, it says that it travels 160 kilometers at 10 degrees south of west. So once again, I'm going to draw a reference line that is west. I'm only going to go 10 degrees south of it this time. So it'll have an X and a Y component as well. So where would I draw a line that represents the total displacement of this plane? Displacement is always the straight line distance and direction from beginning to end, right? So I start here and I draw a line that goes straight to there. Okay, so I'm just going to make it a different color here. Properties. Blue. All right, so now I've got that line which represents my total displacement. Does it also have a Y and X component? Okay, so here's what we have to realize about this line. If I take black X and add it to red X, should that equal blue X? Yes, okay, because in the first part, this 220 kilometer vector, the object did go west. And same thing in the red vector, it went west again. Well, the total amount west it went has to be blue X, right? The same is true for the Y component, right? It went a certain distance north in the first part and then went a certain distance south in the second part. But Y is still the sum of those two numbers. It's just that one of them is negative now. All right, so what we have to do is find red X and red Y and black Y and black X. If we can find those, then we can find the sides of the blue triangle. Right? This is what we call the addition of vector components. The components are the X's and Y's, and we can calculate those because we know the hypotenuse and an angle within these other triangles. And all you need is two pieces of information about a triangle to figure out everything there is to know. And if you know a side and an angle, you can find all the other sides. So that's what we're going to do. Our first step then is to find out what is black X. Okay, what side of the triangle is black X in relation to the 30-degree angle? Is it adjacent, is it opposite, or is it the hypotenuse? It's adjacent. Okay, so if I want to figure out how big it is, and I have the hypotenuse, which trig function do I use to find X? Cos, right? SOHCAHTOA, right? Now I'm going to use cos because it's adjacent over hypotenuse, right? So for X, okay, so sorry, let's line this up. The cos of theta equals the adjacent side divided by the hypotenuse. I know the hypotenuse and I know theta, So if I want to solve for adjacent, what do I do with hypotenuse? Multiply it over to here. All right, so I'm going to solve for x by going cos of 30 degrees times the hypotenuse, which is 220. Whoa. Okay, so black x is 190.5255. Okay, I'm going to keep all those numbers in the calculator. I'm going to round off on the board here, but I'm going to keep all those numbers. Really important that we do, in fact, keep all those numbers. I forget, 190. And that's west. I always write which way it is as well, so I remember for later. So what trig function will I use to get y? Yeah, I can use sine, or basically I could use any function. Now I know two sides of the triangle as well. So, okay, but I'm going to go with sine. Sine of 30 times the hypotenuse, 220, should be 110 meters north. Okay. You guys don't seem impressed that I just did trig in my head. You shouldn't be. The sine of 30 is 0.5. It's easy to remember. That's why I use 30 degrees all the time. Makes me feel good about myself. All right. Now we got to do the same thing for our next triangle for the red ones. Right, we've got to find the x and y components. It so happens on this one that x is again the adjacent side. It isn't always, okay, but in this case it is in both cases, right? So x is the adjacent side, so I'm going to do the same thing I did up here. The cos of 10 degrees this time times the hypotenuse, which is 160, will give me what red x is. Okay, so 157.5692. Right, and again, we want to keep all those decimals for later. And then I got to find red y. Y is the opposite side, so we'll go sine of 10 degrees times 160. So that's going to be 27.87. Okay, and so this is going to be, this one's west, and this one is south, okay, just so I keep those in mind. All right, I want to find blue x now. So what I've done is I found out essentially how far west it goes and in each part, and how far north or south it goes in each part of the trip. So now I need to find the totals. Kind of like what we did with those two-part v equals d over t questions, except now there's more directions than positive and negative involved. Okay. All right, so if I want to find blue x, both the x components went west. So I can just add them together and get the total amount west that this object went. Everybody okay with that? All right, so I'm going to take my 190.5255 and add it to the 157. Okay, and notice I'm keeping all the decimals here. Okay, plus 157. 156.92.405. All right, so that gives me my total x component to be 348.0948. Okay. All right, then I have to do the same thing for y, except one of them is south and one of them is north, so really I'm either adding a negative or I'm subtracting, whichever makes more sense to you. Mathematically, it's the same thing. Okay, so for y here, okay, we're going to take our 110 and we're going to subtract our 27 to get our overall y. Okay, so we got 82.216. Okay, and I'm putting those directions on there. All right, now can I find my total displacement? Okay, what do I have to do next? Right, I have to do Pythagorean theorem. I know the two sides of the blue arrow's triangle, right? I know y and x. If I put them in Pythagorean theorem, I'll figure out the magnitude of the total displacement. All right, so that's my next step. All right, so I'm just going to go blue x squared plus blue y squared square rooted, and that will give me my total, the magnitude anyway, of my total displacement. All right, so the square root of 348.0948293 squared plus 82.216. No, I could have put in answer and saved myself all that time. All right, so my total displacement in this question is 357.67 kilometers. Okay, I'll put in the right numbers, significant digits when I'm all done. Okay, but right now, that's my total displacement. Now I also need to find what direction that is. It's obviously north of west, but I need to figure out how many degrees north of west it is. So I'm going to use trig, and you can use any trig function you want. I'm going to use tan because it's my favorite. Okay, so that's going to be our 82.216 divided by our 348.09. Okay, I'm going to use all the decimals in there when I actually calculate it. All right, so, oh, I did that wrong. Okay, it's okay. I can put them in backwards, but is it still valid? Yes, it's just not the north of west one, it's the west of north one. It's like I drew the triangle the other way. Okay, and that's fine. Just as long as I notice that I did that and put the right direction on it, I'm okay, right? If I put in here that this was north of west, would I get it right or wrong? I get it wrong, right? It's not north of west. This is the one that's west of north. They're complementary, but I have to put the right direction on it. All right. Okay, so my angle, so my angle is going to be, what was it, 76.71 degrees, and that one was west of north. All right. In my original question, I have two significant figures. I used the angles to do calculations. They were only measured to two significant figures, so that contributes to my accuracy of my answer. So my total displacement will be 3.6 times 10 to the 2. I have to put it in scientific notation because I only have two significant figures. Okay, so 3.6 times 10 to the 2 kilometers at 77 degrees west of north, or at 13 degrees north of west. Either one of those would be acceptable as an answer. Okay, when I put that number in scientific notation, I saw a few panicked looks. Okay, do I need to go over how scientific notation works? Okay. We use scientific notation if we have a very big number and we want to represent it as a smaller number, okay? Or if we can't write the whole number because of significant figures. So let's say I have this number here, 123,456, but I only have two significant figures, right? So I can't show the 3, the 4, the 5, or the 6. So I have to represent this as a two-digit number. Here's where the decimal is in that answer. Everybody okay with that? Okay. Our numbering system works on what we call a base of 10. That is, every place in a number is 10 times greater or smaller than the previous one. All right? So if I'm moving the decimal, I'm going to make this 1.2. Okay, I got to move the decimal from here to here, which is 1, 2, 3, 4, 5 places. That's 5 factors of 10. All right, so this number is now going to be 1.2 times 10 to the 5. Okay, I tell people, here's how many places I moved it, so the number's actually this big, even though I'm representing it as a number that's only this big. All right, in scientific notation, proper scientific notation, the number is always between 1 and 9.9. Okay, we always make the number between 1 and 9.99, right? Because I would have some people who would go, well, this is the same number, and mathematically, they're correct, but that's not proper scientific notation, okay? Proper scientific notation, the base number is between 1 and 9.9. Okay. That's how scientific notation works. Everybody okay with that? If I have a decimal, it's similar. Okay, so let's say it's, all right, I want to put that number in scientific notation, so I need to make it a number between 1 and 9.9, which means I need to move the decimal from here to there. So that's 1, 2, 3 places. So this is going to be 2.57 times 10 to the negative 3. All right, after reflected, I moved it that way, and the number is smaller than the number I wrote. Everybody okay with that? Okay, so this is kind of the explanation of what we just did. I always find it's better to see one of those big vector component addition problems done first and then kind of explain what we're doing so you see where we're headed to while we're working towards that position. All right, so I want to learn how to resolve a vector into its components. We did that when we were finding x and y. Okay, so we had the triangles drawn and we found the red x and the red y and the black x and the black y. Those are the components. So finding the components basically just means using trigonometry to find the sides of a triangle. Okay, learn how to use vector components to add vector quantities that are not collinear or perpendicular. That was the end result of that problem we just worked on. Okay, we added two numbers or two vector quantities that were not perpendicular and they were not collinear. Okay, but we could still add them together. All right, so if the magnitude and the direction of a vector are known, okay, so we know how big it is and what direction it's pointing, then we can figure out its components, that is, its horizontal, x, and vertical, y, parts. Okay, essentially we're turning every angled line into a right angle triangle. Okay, that's the easiest way to do it. Okay, that process is carried out with trigonometry, obviously. Okay, so in this case here, on this diagram, A is my vector, so the blue line is my vector. If I want to find the x component of that, okay, which trig function am I going to use there? The horizontal component of this is which side? Opposite or adjacent? It's adjacent to this angle, right? So in that case, I'm going to use the hypotenuse and this angle to find the adjacent side, which means I'm going to use cos. Okay, if I want to find the opposite side, then I use sine. Okay, I have the hypotenuse, I have to use it, so I'm either using cos or sine because they're the two that involve using the hypotenuse. All right, everybody okay with that? So that's kind of what you see here on this next one. So if I want to find the horizontal component on this one, it's cos. On the vertical one on this one is sine. It's not always that way. It could be flipped and then it would be the other way. So if the triangle was drawn like this instead, okay, this is x and this would be theta. Now I would use sine to find that side and cos to find this side. Okay, it just all depends on which way the triangle is drawn. Right? That ringing a bell from geometry? Hopefully. All right, so if I've got this displacement vector, it's 175 meters and points 50 degrees relative to the x-axis, so above horizontal. Okay, we want to find the components of it, right? So to find x, knowing that this side here is 175 meters and this angle is 50 degrees, I'll find x by going cos of 50 degrees times the hypotenuse, which was 175. That will give me x because it is the adjacent side. Okay, and y is the opposite side, so I'm going to go sine of 50 degrees times the hypotenuse, 175. All right, so the x component, so this side here, okay, the horizontal side is 112 meters. Okay, and then the y components, okay, we just go sine of the same thing, so sine of 50. All right, that side's 134. Okay, everybody kind of follow what we did there? Okay, we're always going to have to break up our vectors into a right angle triangle and find the sides. Okay, take a little bit of practice, but I think it'll ring a bell for you and be familiar once you get going on it. All right, I'm gonna leave it there for today. Still got about 5 minutes left in class, but rather than go into any more today, you guys are already looking kind of traumatized. So, okay, stop there.